at the School of Music of the Federal University of Rio de Janeiro. His music has been performed by the Wind Quintet of the Berlin Philharmonic, by the Poznan Philharmonic in Poland, among many other notable ensembles. He has published widely, especially on compositional systems and compositional modeling. And indeed, his title today is Determination of Compositional Systems through Systemic Modeling. So, through the miracles of technology, I give you Professor Pitombeira.
Good morning, everybody. First, I would like to thank the UNAM for the opportunity of presenting this paper here at the Ciencias. My special thank you to Auditorio, who helped me with the transmission and the preparation of the setup for this class. My paper is the presentation of compositional systems through systemic modeling. This is a research conducted in the USMAT research group of the Federal University of Rio de Janeiro, Brazil. This paper described the methodological procedures for the systemic modeling of Monteiro number 1 by Camargo Guarnieri. The purpose of this methodology is to propose a hypothetical compositional system that gave rise to this work. With this system, then we plan and compose a new work for doing the trio. A key concept of this methodology is parametric generalization that will be defined in the paper with other important concepts such as compositional systems and systemic modeling. First, a model is a simplified representation of a real system with the aim of studying systems. In the field of engineering, modeling can offer a physical model, a mathematical model that represents the characteristics of a system. Wait a second, I will put a headphone because there's some reverberation. Can you hear me? Yes, that's better. Good. On the field of engineering, modeling can offer a physical model, a mathematical model that represents the characteristics of a system with high accuracy in order to test its operating conditions and, in particular, its limits. In the music domain, the model of a particular work may be proposed from analytical tools that can describe its structural relationship. However, from a compositional perspective, it is not our interest to propose a comprehensive and multidimensional modeling from which one can replicate the original work in all aspects, since it's not our intention to rebuild and analyze the work, but to build a different one which keeps certain degree of kinship with the original. Thus, systemic model is intentionally partial and only focuses on some aspect of a work. The degree of relationship between the analyzed work can be considered in some respects an text, and the new work happens in the realm of a deep structure called compositional system, which is determined from a series of guidelines that act directly on the construction of musical vocabulary and syntax. Systemic modeling consists of 3 stages. The first stage, parametric selection, we do through a prospective analysis. We've tried to find the parameters that can render best analytical result. The analytical phase will describe the behavior of the selected parameters of the analyzed work. For example, the syntax of the harmonic structure, the profile of melodic contours, the rhythmic patterns, etc. In the last phase, the values associated with these parameters obtained in the analysis are generalized. That is, are emptied of particular values. Thus, for example, if the analysis reveals that the intrinsic structure of a work is built from the parsimonious connections of set classes 012, 013, 014, one can generalize the information stating that the structure is consolidated through parsimonious connections of each class sets. In order to clarify the steps of systemic modeling, we'll take the initial gestures of Weber and Tonzert up to 24. I'll ask Alan to play just this fragment. As one can see, it consists of three-note fragments for oboe, flute, clarinet, and trumpet. Each fragment has its own information on the following parameters: pitch in terms of pitch class and register, rhythm in terms of duration, time points, dynamics, articulation, timbre, and tempo. The first phase of systemic modeling, parametric selection, will select the parameters that will be the focus of the procedure. In this short example, we will only select the pitch parameter. So the first consequence of that, the selection, is that we lose all information regarding the other parameters. So we can see in figure 2, we can verify that the pitch of the Weber acceptor were transferred to a music staff with no other additional parametric information. The second phase is the analysis. We try to find relationships amongst the three-note fragments. It consists of three pitch class sets related by transposition and inversion, which means that they belong to the same set class. Furthermore, they constitute a 12-tone series, which means that we have 12 distinct pitch class form series derived from trichordal class 014. In the last phase, it's called parametric generalization. We will only consider relationships between potential objects or generic objects. This phase is fundamental for the modeling process, as we have laid down here, since it makes it possible to replace the original objects with entirely different new ones following the same relationship. So, following this principle, we plan and compose a new fragment which follows the same rules. Then we go to the systemic modeling of Guarnieri's Ponteo number 1. I'll ask Alan to play this 15 seconds of this. Okay, so this figure shows the first 6 bars of Guarnieri's Ponteo number 1, which has a slow tempo, sorrowful with 32 bars. The macro structure is a loose ABA plus coda. In our analytical methodology, we consider that the work can be divided into 2 layers. The first layer corresponding the right hand of the piano and consists of 7 melodic gestures. The second layer corresponds to the left hand of the piano and is divided into 2 sub-layers. One, a rhythmic figuration that is repeated throughout the entire work, and long notes in a lower register. As the rhythmic feature is not being considered this analysis, the rhythmic configuration are compressed such that the second layer will be seen as a single block or voice. The modeling will be accomplished separately for each layer. For the lower layer, the analysis indicates the chromatic sets in order in which they appear, and not in normal form, and intervals separating each element of these sets in relation to adjacent sets. So this figure shows the pitch class and the parsimonious connection between this pitch class sets. These intervals of parsimonious movements form sets indicated in the figure 5 inside brackets and labeled with letters of the alphabet. So what we did next, trying to find a relationship between the relationships of the sets. And this table was transferred to a Python script. So I could provide a new generator set and a new set of relationships, and it will create the entire lower layer for me. For the upper layer, for the 6 gestures of the upper layer, we found several relationships between all pitch class sets. And the idea was to find, try to find a generator set that could create the entire complex of 6 gestures. So this was transferred to a MATLAB function. Later we can provide also an initial set, and it will build the entire set of 6 gestures for me. So we go now to the compositional plane of germination. Germination was a piece commissioned by the Quintos Terranos trio in Texas. This movement this is the first movement piece. So it started with the Python script. It provided an initial set. It was 7, 10, and 5, and an interval set +2, +1, +1, -1, and it constructed for me the entire lower layer with no rhythm information. Then applied also initial set to the MATLAB function, and it generated the entire complex of gestures. Then I combine both, and I have the first stage of the piece, germination, that Alan could play a little bit. Okay, I think that's it. I had planned 15 minutes presentation. It's 14, so I think if you have any questions, I'm glad to answer. Or I will leave here my contact information. I can send you the scripts, functions and scripts.
Thank you. Are there any questions? We have time for a couple. No questions? Let's thank our contributor from Brazil. Jason, come on up and get set.
Okay, thank you.
Despite our late start, we're more or less on time.
Okay, bye-bye. Thank you.
While Jason is getting set, I'll introduce him. Jason is assistant professor of music, theory and composition at Boston University. He has been publishing prolifically in the major journals, Music Theory Spectrum, JMT, Journal of Music and Mathematics, and he has a book forthcoming from Oxford University Press, Organized Time. Jason is also the founder of the mathematics interest group at the Society of Music Theory. All set? All right, Jason, let's welcome him.
Use the microphone. All right. Thank you all for being here. Thanks to the organizing committee and especially Emilio for putting together such a great conference. It's been wonderful so far. I've enjoyed everybody's presentations. I have the good fortune of following upon some of these Chris's and Daniel's and especially Emmanuel's. I'm going to rely on them quite a bit for some of the background because I do have a lot of material, so I'm going to go through some things a little bit quickly. My presentation today is combining DFT on pitch class sets with some investigation of corpus data about tonal distributions and proposes some ideas about what tonality is and how we might investigate features of tonality. So it's in 5 parts, of which one might be curtailed. I'll do some introductory material about the DFT on pitch class sets and a little bit more about the kinds of qualities that you get out of the DFT, which Emmanuel talked about earlier today. And a longer section that shows a lot of data from tonal distributions coming from a lot of different places in the literature over the last 30 years in this topic. And making the argument that the DFT is a good way to understand what's going on in this data. In the third section, I'll look briefly at another set of data, which is behavioral. So the second section is all corpus data. The third section is behavioral probe tone type of data. And I'll show that that's similar but a little bit different than the corpus data. And the fourth section, I'm probably going to refer you to the written paper for that in the interest of time because it's pretty well explained there. And in the fifth section, I'll introduce this idea of a tonal index, which also comes out of how some regularities we observe in DFTs of tonal distributions. So first about the qualities, diatonicity, which we heard a lot about this morning, and these other two are just new terms for other things we've also seen. So some of the background here, these are some of the important references. The DFT on pitch class sets was first proposed by David Lewin, picked up by Ian Quinn in his follow-up on his dissertation in Perspectives of New Music, an important source, which led to some work that Emmanuel and I have done recently on phase spaces and some other topics such as harmonic qualities. So I have a couple references there in JMT, and Emmanuel's book, of course, is a great consolidation of a lot of this material, which you can see out there. The first thing to know about the DFT is it's a change of basis, so there's no information loss. When we perform the DFT, you're taking a series of pitch class spikes, characteristic function of a pitch class set, and you're transforming it into a series of periodic functions of which you have, you can think of them as magnitude and phase, or you can think of them in complex space. If we think of them in complex space, there's a kind of a fast and dirty way to calculate these things. So the pitch classes are all unit vectors in complex space. This would be for the fifth coefficient. And you can isolate the pitch classes of your set you're interested in. You can add them together and as vectors, and the result is the position of the pitch class set you're interested in. Then the magnitude is the distance from 0, and the phase is the angle from 0. So for instance, if we were to take, there's all of the pitch classes and all of the 6 non-trivial coefficients. You can isolate, say, all of the elements of the C major triad and add them. You see that in certain places you get something very small. C major triad is not very chromatic, but on the 5th and the 3rd and the 4th coefficient, you get something fairly far away from the origin, right? So this is how this works. We can investigate the 3 components, coefficients that I'm going to be particularly interested in today are diatonicity, which again we heard a lot about this morning. So in this case, things close together in similar keys, similar diatonic areas, and diatonic scales are large. Triads are fairly large, but not quite as large as diatonic scales. C major triad is in the same place as its dominant 7th for the key of C major. The 3rd coefficient, which I'm going to call triadicity in this case, we might call it something else in non-tonal contexts. In this case, triads and 7th chords are larger than diatonic scales. Everything is present here, though, and the way things arrange in phase in this component is more related to their voice-leading possibilities, their triadic voice-leading possibilities. So here, a C major triad is very far away from a G dominant 7th because they are different functions. Emmanuel said this morning that I refer to the second component as chordal quality, which is completely accurate, and now I'm doing something different, calling it diaticity. The chordal quality is a very good thing to call it in a non-tonal context, but in a tonal context, obviously these terms are not quite fixed yet, but diaticity seems to be a good way to think about how this component works. It turns out to be the other important component in tonal distributions, which is why I'm interested in it. And here you see that again, the major triad and its dominant 7th are together. What you get is things are close together if they have similar roots. So a position here is determined by its root in 5th. Nothing is very large amongst these kind of common tonal sets in this space, but they're all, in fact, they're all unit vectors in this case. So with that little bit of introduction to the idea of a DFT on pitch class sets, I'm going to move on to some data. I'm going to throw a lot of data at you here. But before I do, I'm going to show you a picture that you're probably familiar with on the left, which is the Krumm-Hansel and Kessler tonal space. And this space was initially created by means of a multidimensional scaling on behavioral data. But Krumm-Hansel later realized that you could generate it with the DFT on the 3rd and 5th coefficients, the phases of the 3rd and 5th coefficients. She explains this in her 1990 book. And this is a tone nets from my 2015 article, so we can see that these two things are essentially the same. The thing we get from the behavioral data by correlating behavioral data, if we just do a few simple transformations on that, we get the same arrangement of major and minor triads or keys or whatever you want to plot in these spaces you can. So if I take a bunch of corpus data, this is from a bunch of sources, some older ones, some more recent ones like Temperley and Prince and Schmuckler, all grouped together. And you see that if I put it in a space defined by the phases, right? So positions of the 3rd and 5th coefficients. So the 5th coefficient diatonic phase on the vertical axis, 3rd coefficient triadic phase on the horizontal axis. They all cluster around the triad, which is the tonic of their key. And you see if I transpose this all around the space, everything would be clear what key is determined by each of these points, which is how a key finding algorithm based on tonal distributions works. If I zoom in, you can see where all of the individual things fall. This is, of course, transposed to C major, C minor. You also notice that that thing labeled CBMS is a handmade distribution by Davy Temperley for the purpose of key finding algorithm, and that actually isn't quite as, it doesn't quite match up perfectly with the corpus data. You can see that it's a bit of an outlier. The same thing with the Krumm-Hansel-Kessler profiles, which are not shown here, but will be later. We could do the same thing with, right, okay, so this is another set of data. This is breaking up the Prince-Schmuckler data, which is a pretty big data set by composer. So you can see even when we break it up by composer, we get a similar kind of clustering. And that suggests maybe we can do some investigation of stylistic information based on this procedure, which I'll talk a little bit about. It's not dealt with in this paper, but will be in subsequent work. So we could do the same thing with the second dyadicity and the fifth component, and things work out pretty well there too. You see that things cluster around their tonic triad. We zoom in on the space, you can see where individual things fall. And we can also break it up by composer if we use just the Prince and Schmuckler data. And again, they're clustered. The only one thing you notice is that C major is actually not exactly centered on its, sorry, C minor is not exactly centered on the C minor triad. So the triad is not actually a perfect representation of that, those distributions, but C major actually works pretty well. Now you might think, well, then can I just do this with any phase components? The answer is no. Here's the first and the fourth, and you see that this data is very inconsistent. We're looking at data points here that come from a bunch of different articles from with a wide variety of methodologies, different kinds of corpuses. So the fact that they all agree so closely is a strong result. But if you put them in the wrong space here, then they don't. They kind of just a mess, right? So they're, you know, it looks like the C major data looks closer to a C sharp minor triad than anything else, right? So it's not, it is important to choose the right components, and this is why. So here's the Prince and Schmuckler data. On the left-hand side, you see the power spectra of these, which are the squared magnitudes. And on the right, the phases, let's look mostly at the power spectra now. This is like what Emmanuel was showing this morning with the qualities. These are the qualities of distributions, and you see that very consistently diatonicity is overwhelmingly, by many orders of magnitude, the most important quality in all these distributions. So by doing the DFT, what we're doing is isolating a big chunk of the information of those pitch class distributions in one place, the diatonicity. There's one exception. So if I say the rule here is that, you know, first you put the fifth component up here, and then at another order of magnitude down the third, and then close to a little bit below that the second, and then everything else is just spare change at the bottom, right? That's true of every single composer, with one exception, which would be Liszt. So Liszt is actually a very interesting case. And here we see that the diatonicity and the triadicity are approximately equivalent. So that's the only exception to that rule. And it actually turns out to be a real property of Liszt's music. This is a small corpus when you break it down for Liszt and Brahms and Scriabin, but it turns out to be something like this turns out to be true of Liszt overall. He's a special composer for the 19th century. And on the phases, we can also see the consistency of the phases in those particular components as opposed to the others. Same thing with minor key data. Again, diatonicity, very important. Triadicity, also important. And then a close third is the dyadicity. The other ones don't figure in any significant way. So that's a pretty strong result. What we're doing is filtering out a whole bunch of information from those pitch class distributions that isn't relevant, apparently. So this is more recent, just a little preview of some more data I just finished collecting with the help of a student at Boston University, Matthew Chu. This is from the Yale Classical Archives that Chris talked about yesterday. And I'm just showing the power spectra here. Again, you see the rule that I explained to you before. This is now with 33 composers from the Yale Classical Archives, from Bird to Rachmaninoff. And not only do you see that the diatonicity gradually decreases over time in a pretty impressive way. This isn't scaled by date, but it's in date order. Bird is actually will be like way over here if you scale it by date. And you can even see, you notice that there's, you know, sometimes there's a little dip in the curve. that basically corresponds to all the composers we think of as advanced harmonists for their time. You got Bach, Scriabin, Beethoven, Schubert, Liszt. And you see Liszt is the most impressive dip in the diatonicity curve. So that it basically indicates this is for averages over entire pieces of music. So what you're probably seeing there is a tendency to modulate to distantly related keys, is what I would suppose. Minor key data, basically the same story, except that the diatonicity is a little lower, triaticity is a little higher overall. This is the case now in the minor key data, where Liszt in this database has equal triaticity and diatonicity. For some reason, it happens in minor here. In Prince and Schmuckler, it happens in major. I'm not sure why. We can also look at historical trends, and this is just in complex spaces. These ones basically just show that the blue, the 16th century composers, are a little more consistent than the others. But you see, if you look at, here's a suggestion that the fourth component might actually be interesting in some way, because you do see a historical trend from blue to red to green. And the diatonicity here, again, this is in complex space, so now the magnitude is how far away from zero you're getting. You see you gradually get closer to zero as you get towards the 19th century, blue, red, green. All right, so, so next topic, behavioral data. These are these kind of probe tone experiments where you play some tonal context and you ask a listener a bunch of questions about which notes sound the most stable in that context, and then you get a distribution from that. So you can also plot these in phase spaces, like I've been doing with the distributions. Krumhansel's claim, initial claim about this, well, a persistent claim about this over time, has been that the corpus data should match the behavioral data because there's a cognitive process whereby we are learning the statistical information out of music we hear, and that is predetermining our expectations about what we should expect to hear in a given context. I think that that's true, but we can qualify that. If we have the DFT, we have a more powerful tool for seeing what exactly is going on in this data, and it gives us a picture in which Krumhansel's claim is true, as she showed in a number of papers, but not 100% true. There are some differences between the behavioral data and the corpus data. And you can see that if you just look at this chart. This is behavioral data from a whole bunch of sources. We've got the original Krumhansel-Kessler, Cuddy and Bedertscher, tried out a number of different kinds of contexts to see if that held up. Same thing with Brown, Butler, and Jones. They tried to mess with the context to see if it screwed up the profiles and their correlation with the keys. And then we have some Yanada et al. And Smith and Schmuckler, more recent articles with different kinds of paradigms. I'll have to refer you to those if you want to know what they did. But basically, it doesn't matter. All of these different paradigms give us basically the same result, which is that these spread out a little bit more, but most of them are going to correlate with C major better than anything else. So they are close enough that a correlation will tell us what key the listener was perceiving. But you notice that not only are they a little bit more spread out than the corpus data, but they're also in a different place. They're not exactly in the same place. The corpus data tends to be a little bit towards the dominant side of its home key triad, just a little bit, whereas the behavioral data tends to be well towards the subdominant side, to the point where actually in some of those Brown, Butler, Jones experiments, the listeners were actually perceiving F major, apparently, when they heard a C major triad. I can only speculate about the reason for that, but I think it has to do with temporality. The corpus distributions are non-temporal. You're just averaging over a period of time, whereas the probe tone experiment is inherently a temporal question, right? You're asking how does this tone fit in this context, but the tone is always following the context. So implicitly, you're asking how does this tone follow this context? That temporal order tends to make us want to move in a subdominant direction, I would argue. Okay, so this is the part that I'm going to just flip through for the interest of time. So basically, the lesson of this, which, and you can look at the written paper when it's out, is that we can use the DFT to answer a question asked by Albrecht and Shanahan, which is that why don't we use Euclidean distance instead of correlation for key finding algorithms? they found that Euclidean distance works better for minor keys. We can explain this mathematically. Basically, if you have the exceptional cases, Euclidean distance is biased towards the minor because it has a smaller overall diatonicity. I have some examples. These are all in the paper. So if you look at the pitch class profiles here, it's because that minor key profile is a smaller diatonicity that therefore Euclidean distance is more biased towards the minor, because Euclidean distance under the DFT remains Euclidean distance. As Emmanuel showed us this morning, correlation becomes multiplication. And when you multiply two things with high diatonicity, if there's not enough other information to orient you, you'll just choose the best major key instead of being able to distinguish between major and minor. So one last topic, we have this. So I've argued so far that we're limiting, by using the DFT, we're limiting the significant information from 12 to essentially essentially 6, right? So the magnitude and phase of the dyadicity, triadicity, and diatonicity, right? So we're reducing our information by half what's relevant to tonal music. Actually, we can cut out one of those three in a certain sense by means of this rule that seems to hold in tonal music, which is that there's a linear constraint on the phases of these components. So in the mathematical sense, right, this is a change of basis, therefore mathematically these are independent, right? Totally independent mathematically. But it seems to be the case that to write tonal music, you impose some kind of linear dependence between these, which is that the sum of the second and third phases minus the phase of the fifth coefficient is equal to 0 or close to 0, right? So we have a tendency to want to keep that close to 0. That happens to be true of single pitch classes, of fifths. It's absolutely true. Diatonic scales, again, equal to 0. With major and minor triads, depending on whether it's major or minor, you're a little above or below 0. The same thing with distributions. The major distributions would be a little below, minor a little above, but they're all very close. That's from the Princeton-Schmuckler data, but it would hold up for anything. So I'm going to show you a few examples of these. And I have to thank Richard Plotkin for helping with the Python code that was used to generate these examples. First simple example from Mozart A minor piano sonata is probably familiar to you. This is interesting because it has a diatonic circle of fifths. I'll play that. That's pretty quiet, right? Is there any way to get more volume on that? Yeah, I have my volume to the max here. Okay, so notice that our values are all close to the values for an A minor triad right there. And what I've done is I've spread this out so that we can see the cycles. So it's going, both the green and blue lines, which are the dyadicity and triadicity, are going from 0 to 0, right? So I've unfolded the space so that you can see the cycles. And here, the circle of fifths makes them move in opposite directions. And so what happens is that even as those things are making a big journey, the tonal index just sticks at 0. Because it's a diatonic cycle, that purple line, which is the diatonicity, the phase of the diatonicity just remains constant. So this is just a windowed DFT of this MIDI file. Another example from just a short piece of Corelli's. So you go from D minor to the relative, and then to get back in the second part, he has an ascending fifth sequence. So it's the sequences that do the interesting things here. So here's just the first line of that. You have, here's D minor, and you notice at the end that the blue and green move out a little bit, and that's because they're moving towards F major, which looks like this. Okay? So you see how they're moving from D minor to F major. And that involves a visible move in blue and green, but in a very small move in purple, which is the diatonic. So something interesting happens at the end, right? We get back to D minor in a different fashion with that ascending fifth sequence. That makes the green and blue move in the same direction. They're still going from D minor to D minor. Did I have this in there? No. So it's our ascending fifth sequence there. But they cause a cycle in the in the tonal index because they're moving in the same direction. It's because it's an unusual ascending sequence. And the lesson here is that that thing wants to stick to 0 basically in tonal music. This seems to be what's going on here. And if the composer pulls it away from 0 with a sequence, it's going to quickly try to find it. It's like a magnetism of the 0, right? And it's going to hit it again somewhere else. Here's a longer example. I'll refer you to the paper for this. It's got a bunch of different sequences in it. That's what makes it interesting. Another Corelli example from one of the violin sonatas. So I'm gonna skip through this one. You can kind of watch it go by here. There's the data because this will be in the paper. And you can see there's some cycles in the tonal index that happen when the sequences occur. You can also trace the change of keys in this data. And an example of enharmonicism, this is where you get cycles in the 5th component. Yeah, I should breeze past this one, just get to the conclusions. So this is a piece that modulates through a series of keys that ends up enharmonically back to where it began, but with a respelling. And you can see that in that the purple line going, making a cycle over the course of the whole piece. So this is a very long example here. And you can see the changes of keys along the way also. Okay, so to summarize some of the things I've talked about and some of my claims here, first of all, you can think of, because of the prominence of these components when we're looking at tonal distributions, one way to think about tonality might be as a kind of bandpass filter for tonal information, right? By applying the DFT and then removing inessential information. What I mean by inessential is tonally inessential for what key we're in or what the tonal implications of the music are. We get a tonal hearing, essentially, of that music. So you might say that tonality is maybe a feature of the music, but it's also a way we perceive the music, which is by filtering out the inessential information. That's maybe an interesting, suggestive proposal. Because of that, we can just look at 3 phase components, and tonal closeness and distance will correspond to tonal closeness and distance in those phase components. So, but what we basically end up with is a 3-dimensional toroidal space that tells us where we are in proximity to various possible keys, right? Because of the linear constraint, what we have is a plane in that 3-dimensional space that describes a stable tonal position, right? So we can also project that plane onto one of the axes of the space and get a 2-dimensional representation like the Krumm-Hansel-Kessler space. And finally, we have the place where we move off of that tonal plane happens to be in sequence-like progressions or sequences. And I would argue that that's an essential feature of that harmonic process, which is essentially different than other harmonic processes like cadence or establishing a key. That sequence is special because it creates this instability that makes us unsure about how we're going to remagnetize to the tonal plane. So some examples of circle of 5th sequence, that actually keeps us on the plane, so that's different. Ascending stepwise sequences, though, that makes us go off the plane. And harmonicism are cycles in the 5th coefficient. So we have lots of different kinds of cycles that are potentially interesting for understanding what's going on in music and time. And that's all I have for today. I took the printed scores and I made MIDI files of them and then used those. The algorithm runs on XML, so I transferred MIDI to XML and then ran it on those. So I used the printed scores initially, yeah. Yeah, Thomas? Mm-hmm. Mm-hmm. That's interesting. Is that in the dissertation that I have listed up here? Yeah. Thank you. Yeah, I have to look at what he did there. Yeah. Exactly. Yeah, that's an interesting proposal. So the first thing I'd say is that, well, the first next step here is just working with this better data set and getting a bigger picture with the Yale Classical Archives. But the next thing I'm interested in is these distributions are atemporal, and I've already showed that there's certain things about how music moves that we can also look at with this, and so I want to look at that maybe not rhythmic but temporal information, as in, you know, are there rules about how we can move within this space, and so that's another project. I think you're asking something more abstract about dealing with rhythm, and you can do the discrete Fourier transform on rhythms. So that's potentially an interesting topic. It's very different than this. You'd have different problems, different results, but I think it would be very interesting, especially on music that's oriented around rhythmic patterns, like a lot of Latin American music. That would be a really interesting topic. And I would refer you to Emmanuel's book because he looks at rhythm and pitch through the DFT, and that would be a starting point for seeing how it works on rhythm, on beat cycle. Yeah, that would be another step after that, maybe. Yeah. Yeah. Oh. Sure, one more? One more. Mm-hmm. I don't know if I can give the complete explanation of that quite yet. You and I, between the two of us, I think you made the observation that that this has to do with being a generated set, right? So there's some mathematical things we can say about why this kind of equation holds true of pitch classes and also generated sets. So that might have some bearing in the explanation. Basically, by having those three things line up, you might think of it as lining up your root with your triad. So the triadicity tells you where you are on the circle of thirds. Within the diatonic scale is determined by your diatonicity. And this constraint is lining up the root of your prominent fifth. So it fits the place you are in the triadic cycle, and where it would mess it up if you went off of that. So a good example where it gets exactly opposite is a pentatonic scale. It turns out a pentatonic scale has a total index of 6, which is the furthest away you can get from 0. So that gives you an idea about how, when you have the fifths not lining up with the triadic properties of the scale within a diatonic context. Yeah, so sorry, the mathematical result is that generated sets are either 0 or 6, yeah. So if they're likely to be 0, yeah, that's right, yeah.
It's my pleasure to introduce Grégoire Genuys. He pursues the PhD, if I'm correct, with the music representations team at IRCAM. He's affiliated with l'Université Pierre et Marie Curie, Université Paris Diderot. He's recently been involved in non-commutative homometry in the dihedral groups, and that is actually the topic of his talk today. While he gets set up, I'll mention his co-author, Alexander Popov. He's known to us, or to many of us, for his contributions to prior MCM. Can we have some technical assistance here?
Just the adapter, which
yeah, the adapter, or yeah. Here comes our guy. But anyway, maybe you can. Or. Our assistant will help here. All right, and I'll just carry on here. So, Alexander is known to many of us for his contributions to previous conferences, including the last one in London, and papers in Journal of Mathematics and Music, and he's the author of Towards a Categorical Approach of Transformational Music Theory. So, in a moment, we will have, here, Homometry in Dihedral Groups.
Hello, I'm Grégoire Genuys. I'm glad to present my work here today in this conference. So it's a collaboration with Alexander Popov, who is unfortunately not here today. I will talk about homometry in the dihedral groups. There are many studies about homometry in Zn, which is a set of the integers modulo n. As we saw in these last days, an integer in Zn can be musically interpreted as a pitch class, and then a set in Zn can be seen as a melody. Zn is a commutative group, which is not the case of the dihedral groups, which are non-commutative. Then studying homometry in this group is a new and challenging problem that needs a new mathematical approach. By a musical point of view, it opens new perspectives, since it concerns homometry between chord sequences and not between melodies. Here's the plan. I will first briefly recall what is the Z relation, which is homometry in Zn, and describe homometry in the neo-Riemannian groups. Then I will give a characterization of homometry in the dihedral groups and give a musical interpretation to it in relationship with the neo-Riemannian groups in the case where n equals 12. Then I will define the concept of lift, which is a central concept that builds a bridge between homometry in Zn and homometry in the dihedral groups. And finally, I will present the main results of this work. First, the Z relation is homometry in Zn. If you take two subsets A and B in Zn, you can define two functions. The first one is the interval function between A and B, which is equal for a fixed k to the number of pairs A and B, such that the difference between A and B equals k. Then you can define the interval vector of A as the interval function between n and itself. And we say that two sets A and B are homometric, or also Z-related if they have the same interval vectors. That means that they share the same set of intervals. Homometry is invariant under the transpositions TP and inversions IQ. That's why we say that two sets are non-trivially homometric if they're homometric and not related by transposition or inversion. Here's a very famous example with the all interval tetrachords, which are Z-related. We can generalize the concept of homometry to any generalized interval system. We saw yesterday different definitions. In fact, a generalized interval system is equivalent to a simply transitive action of a group on a set S. Then if you have a simply transitive action, you can define for a set A in a space S and for an element K in the group, the interval vector of A, which is equal for this K to the number of pairs A and B, such that K sends A to B via the group action. And then we can define homometry for any simply transitive action. We say that sets are homometric if they have the same interval vector. For instance, here we can consider the two neo-Riemannian groups, the TI group and the PLR group. They both act simply transitively on the set S of major and minor triads. So we can define two functions intervals between triads. For instance, between C minor and E flat major, the interval in the TI group is a transformation, is inversion I10, while in the PLR group is obviously the transformation relative. So in this context, we can study homometry for the two actions of the TI group and the PLR group on S. Here is an example of two homometric sets for these two actions. We can see them as two chord sequences between triads. At the top, we picture the intervals between those two sets in the TI group, and at the bottom, the same the intervals in the PLR group. It's interesting because those two sets are homometric for the two actions, which is quite specific. I said that I was interested in studying homometry in the dihedral groups, and here I explain why. In fact, the actions of the TI group and the PLR group on set S can be seen as the left action and the right action of the dihedral group D12 on itself. I will explain why in a few minutes, just before I will describe briefly the dihedral groups. So the dihedral groups Dn is the group of symmetries of a regular n-gon. It contains n rotation and n reflections. It is also the semi-direct product of Zn by Z2, where Z2 is the group with two elements, plus and minus one. Then an element is in Dn is a pair k epsilon, where k belongs to Zn, epsilon equals plus or minus one. Here we have the multiplication law in the semi-direct product. That makes Dn a non-commutative group. As a non-commutative group, it acts on itself simply transitively by left or by right multiplication. That gives 2 GIS. Then we can define two functions intervals, one for the left actions. For instance, here between there's two pairs. The left interval is a pair that we have to multiply on the left with k1 epsilon 1 to obtain k2 epsilon 2. And similarly, we can define the interval for the right multiplication. Then we obtain two interval vectors, one for the left action and one for the right action. And we can study homometry for in the dihedral groups Dn for all n. To come back to the relationship between homometry in Dn and homometry in the neo-Riemannian groups, it's a bit long. Here are some identifications. The first one is a non-canonical between D12 and S. We can identify the pair S plus 1 to the major triad whose root is S, and S minus 1 to the minor triad whose root is S. Yes, the action of the TI group on S can be seen as the left action, the left multiplication in D12. To see why, we have to identify the pair P plus 1 to the transposition TP and P minus 1 to the inversion I P minus 5. For instance, if we want to calculate the transposition T7 of D flat minor, we have to do this multiplication. The first pair is 7, 1, which corresponds to the transposition T7. On the left, to the pair 1 minus 1, which corresponds to the triad D flat minor. And we obtain, obviously, the pair 8 minus 1 with the multiplication law, which is a flat minor. We can do other identifications to see the equivalence between the action of the PLR group and the right multiplication in D12. Then it gives a musical interpretation to homometry in the dihedral groups for the case n equals 12. But in fact, we can give musical interpretation to homometry in the end for all n.